Okay, we are recording. Yes, we are doing 3.3 and 3.4, mean, variance, and standard deviation for grouped data. Okay, so groupings. So we started already with our mean, and we're looking at samples here. So the mean is the sum of m times f over n, okay, where m is midpoint, f is frequency, and n is sample size. So the variance is going to be s squared equals the sum of m squared f minus parentheses the sum of m f squared over n, and then all of that over n minus 1. And then the standard deviation will just be the square root of the variance. So the standard deviation is going to be s equals the square root of s squared. All right, then population, we'll do that one in a different color. We'll do blue. All right, so population, we're using Greek alphabet lettering. So you're going to have, the mean is going to be mu equals the sum of mf, but over a capital N. So over here in our key, we're going to put capital N, stands for our population size. All right, and then the standard deviation, the variance, okay, sigma squared equals sum of m squared f minus parentheses the sum of mf in parentheses squared over n, and then that whole thing over n. And then the standard deviation is going to be the square root of sigma squared. Question, do we need to memorize the formulas? No, you do not. You will be given a formula sheet with your test. You just need to know how to use them when given to you. And you need to know which one to use. Am I using a population formula or am I using a sample formula? All right, so what we're going to do is we're going to do some exercises with these. So we have for the data set given here, find the following. N, so N is going to be your sample size. It's a lowercase n, so they are telling us in this case that this is a sample, just in case we need that. Okay, because we have a lowercase n. If it were a capital N, they'd be telling us it's a population. So how many values do we have here? You can go ahead and type it in the chat box. 15, very good. So we have 15 values. That's going to be your sample size. Then we want to find the mean, the median, and the mode. So probably quickest to just do the mean, median, and mode by hand here, and then to make a list, because it's only 15 values. So I'm going to pull up the calculator. And for the mean, let's go ahead and add everything together. So I'm just going to type these in. 20, 10, 19, 11, 18, 20, 18, 10, 11, and 15. All right, so I add them all together, I get 225. So the mean is going to be 225 divided by 15. Okay, so the sum of all of my values divided by the sample size, and that should give me 15. All right, the median, what we are going to want to do is put these in order. So let's see here. My smallest number appears to be 10. And I'm going to have that 2 times. Then I've got 11, 1, 2, 3, 4 times. Let's see, 12, no, 13, 14, then 15, 16, no, 17, I've got 3 18s. Then I have 2 19s and 2 20s. Okay, so my data is put in order, so now I want to find that middle number. So there's 15. So if I divide 15 by 2, that gives me 7.5. So I'm going to count 7 from each of these sides. So 1, 2, 3, 4, 5, 6, 7. So then this is my next value right here. And from this side, 1, 2, 3, 4, 5, 6, 7. All right, so the middle value is 15. There's 7 on either side of it when this is ranked. So median will be 15. And then my mode, which one occurs the most here out of all my numbers? 11, good. Okay, so our mode is going to be 11. And let's just say we wanted to find the range. Do we remember how to do that? You're going to do, yeah, 20, your highest number, 20, minus your lowest number, 10. So our range is going to be 10 there. All right, so we have for the sample below, find the range, the variance, and the standard deviation for, let's see, the distances jumped in feet by 9 long jumpers. So let's see what we've got here. So we've got our distances of 9 long jumpers. It is telling us that it's a sample. This is not grouped. So this is actually going back kind of a review of what we did in 3.1 and 3.2. So we're going to go over that. Let's go ahead. Yeah, we can do this one by hand and in our calculator just to go over. So let's see. Our N, how many long jumpers are there? 9. Yeah, they're telling us there's 9. They're telling us it's a sample. Our range, my highest value is, let's see, 21. My lowest value is 10. So my range is going to be 11. And then this is going to help me. So just one thing here, when we're doing the standard deviation problems, you're always going to ask yourself these 2 questions. So first of all, am I grouped or ungrouped? Because now you're going to be given both. Okay, so this is ungrouped because you have singular values. And then is this a sample or is it a population? And then this is a sample. Yeah, they're telling us in here that it is a sample of distances in feet of 9 long jumpers. Okay, so we could fill in the table. I find it best when we're doing the table to kind of put it in order just to help us out here. So I'm going to start with my smallest values, 10. So I have 10s here, then 11, 12, let's see, 14, 15, 17, 18, and 21. Okay, so we want to use the formula for sample, standard deviation, that's going to be S squared, and it is ungrouped. Okay, so this is from 3.1, or sorry, 3.2. Sum of x squared equals the sum of x squared over n, and then all of that over n minus 1. Okay, so that's the formula we're using. So let's go ahead and start filling out the chart. All right, so we want the sum of our x values. So I'm going to add all of these values. So we're going to go 10 plus 10 plus 11 plus 12, plus 14, plus 15, plus 17, 18, and 21. So that's going to give me 128. Put that right there for my sum of x. Okay, then I'm going to have, let's see, x squared values. So 10 squared is 100. 11 squared, 121. 12 squared, 144. 14 squared is going to be 196. 15 squared, 225. 17 squared, 289. 18 squared is 324. And then 21 squared is 441. All right, I'm going to add all of those values to get my sum of x squared. All right, so it's going to give me 1,940. So I add this column together. And then I also have here the sum of x squared. So that's taking this 128 and squaring it. So that's what we're doing here. We're doing 128 squared. We can put that in our calculation as well. So 128, here's my squared button. So 16,384. Okay, and then I can plug all of these formulas, or sorry, these numbers into the formula here. And that'll give us our variance. So we have the sum of x squared, that's here, the 1940, minus the sum of x values squared, that's the 16,384, over n, our sample size, which was 9, and then that's over 9 minus 1. All right, so what I want to do here, I can add some grouping symbols just to help me with order of operations. I'm going to do the top first. In the top, I want to do the division before I do the subtraction. So that's going to give me, let's see, 16,384 divided by 9. And then I'm going to do 1940 minus that number. So I'm going to go minus second answer, which is the second of the negative sign, and then enter. So that's 119.5, and then I'm going to divide by 9 minus 1, which of course is 8. So I just hit divide by 8, and that gives me 14, and we'll do 3 decimal places, so 14.944. So that's the variance. Then to find the standard deviation, I'm going to take the square root of that number. Okay, so I'm going to come to my calculator and I'm going to go second square root, second answer to pull this down, enter. That's going to be 3.866. Okay, and then we can take this data and we can kind of, well, actually, let's go ahead and check it in the calculator just to go over that again. Is everybody still following me? You guys can give me a, I think you can do it like a thumbs up or something in here. Yeah, there you go. Cool. Okay, so we're going to put this in our list. So we're going to go to Stat and then Edit. And then I'm going to enter this in L1. If you already have something in L1, scroll up, hit Clear. Do not hit Delete because you'll delete the entire L1. So hit Clear and then Enter, and it'll clear that for you. So I'm just going to enter these X values as I have them written down. Yes, I will in just a second. So 10, 10, 11, 12, 14, 15, 17, 18, 21. Okay, so I have everything entered into the list. I'm going to go back to the home screen. So see this in yellow, it says second quit. So second quit to go to the home screen. Then I'm going to go to Stat. Then I'm going to scroll over to Calc to highlight Calc, and then Enter for the one variable statistics. And then there I want L1. So I can either grab it doing second list, or I like to use this one here, the yellow above the one, second one, to give me L1. And I'm going to hit Enter. And that's going to give me this information here. So I have X bar is 14.2, my sum of X squared. Then I have the two standard deviations. So the SX, that's your sample standard deviation. Sigma X is your population standard deviation. The calculator is giving you both because the calculator doesn't know if this is a sample or a population. So you have to determine which one you're using. So here we know it's a sample, so we're going to take the 3.866. Okay, so what this information is telling us, you have that X bar of 14.2. This is in the context of long jumpers. So we could take this and we could say, based on this sample, so based on a sample of 9 long jumpers, okay, they jumped an average, or the average jump. That was that X bar I pulled from the calculator, which was 14.2. With a standard deviation of 3.866. Oopsies. There we go. 866 feet. Okay, that is what the context of this problem is telling us. Now, Christy asked to go over just how to pull down the answers. So in my calculator, if I'm just doing a problem like I've got 7 plus 6, and then I from there want to subtract or do something with that, then you don't need to actually hit anything. You would just go like -4. It'll automatically pull it down. But let's say you want to take the square root of that number and you need an operation before you do that. You just go, so you do your operation, so square root of that number, second square root, and then the answer to pull it down is right here above the negative sign. So you would do second negative ANS right there. So second negative, and then enter. And it will do whatever operation you tell it to from your previous answer. So it pulls whatever the line above it is. All right, any other questions before we move forward? All right, we're going to do grouped data. Okay, and look, it's telling us it's grouped and it's from a population. Okay, so grouped population. So we need to note those first, and then we're going to do the problem. So this is the commuting time. I think the problem, it's from the book. It is from some certain company, so we'll just say from X company, the commuting time of the employees. I believe that's what it is. They surveyed the employees, how long does it take you to get to work? What's your commuting time? So you have from 0 to 10 minutes, 10 to 20, 20 to 30, 30 to 40, 40 to 50. And then you have your frequency distribution. So we've got to do a couple of things with this. First thing we need to do is we need to find how many people were in this. It's a population, so it's all of the employees at the company, how many there were. So we're going to add these. So 6 plus 10 is 16, plus 3 is 19, plus 9, yeah. So we get 30 here. So 30 people. There are 30 people at the company. So that's your population size, your N. Then we need to find the midpoints. Does anybody remember how to find the midpoint of grouped frequency? Okay, so I'm getting silence here. So we're going to say lower, it's the lower limit plus the upper limit, divide by 2. Yeah, it's the limits, not the boundaries though, because the boundaries are going to be a little bit different. So it's just these numbers. So yeah, 0 plus 10 divided by 2 would be 5. So it's just the middle. It's the average of these two numbers. Middle of 10 and 20 is 15. 20 and 30, 25. So these are easy ones. 35, 45. Okay, so the average, this is your lower limit. This is your upper limit. Okay, and then we have, so we need all of these values to use our formula, which I'm going to go ahead and we'll write out the formula again for our variance and our standard deviation. So it is a population. So sigma squared equals the sum of m times f. Nope, it's m squared f, just kidding. M squared f minus the sum of mf squared over n, and then all of that over n. Okay, so let's get those values. So you have midpoint times the frequency. So you're doing this column here times this column here. So 5 times 6, 30, 15 times 10, 150, 25 times 3, 75. 35 times 9 is going to be 315. And 45 times 2 is going to be 90. Then I'm going to do the sum of m times f. So that's going to be, let's see, 30 plus 150 plus 75 plus 315 plus 90. So 660. Okay, the next thing we need is m squared f. So you could do m squared. You can make a separate column for that if you wanted. Typically what I do is I just go like this. So I've got 5 squared times 6. Okay, so m squared times f. And just going to do it like that. So that gives me 150. And then you've got 15 squared times 10. That'll be 2250. Then 25 squared times 3, 1875. Then 35 squared times 9. We're going to get 11,025. And then 45 squared times 2. So 4,050. Okay, and then we're going to find the sum of this column. So let's add these together. So you have 150 plus 2250, 1875, 1125. All right, so I get 19,350. So my chart is filled out. So let's go ahead and find these. You have the mean, the variance, and the standard deviation. All right, so the mean, actually, the mean with group data is a little different here. Again, remember the formula here for population is going to be mu sum of mf divided by n. So if I take this data, the sum of mf we found to be right here at 660, and my n was 30. So 660 divided by 30, 22. All right, so the average here is 22. So we can say at this company, the average employee commutes 22 minutes. Okay, that's the average time. Now let's find the variance and the standard deviation. So here's my variance formula. So let's see, we're going to have sigma squared is going to equal the sum of m squared f. That's right here, 19,350. minus the sum of MF squared. We didn't find that, so we'll write this as 660 squared in parentheses divided by n, which we found to be 30, and then all of that divided by 30. All right, so order of operations on this, I'm going to want to do this, then I'm going to do the subtraction, and then I'll divide by 30. So follow in my calculator. So we're going to go 660 squared. We're going to do that first. Okay, then we're going to divide by 30. So just hit divided by 30, enter. Now you're going to do 19,350 minus this number. You can type it in, it's not that long. And then divided by 30. So that's going to give us 161. That's my variance. My standard deviation well, I'll put it back over here just for the purpose of the worksheet. Okay, so the standard deviation is going to be the square root of the variance. So we're going to do the square root of 161. So second square root, you can just type in 161 because it's a nice number, or you could do second negative to pull the answer. And we'll do 3 decimal places, 12.689. Okay, and what does this mean? So this means that, I'm going to type it in, it's a little easier for me. It will let me do a type. Okay, so at, we'll say X company, the average employee, or the average commuting time, for employees, we'll say for all employees because it was the population. Oh, geez. Is 22 minutes. That was that mean. With a standard deviation of, I can't type. Yeah, that's not even going to help me there. Deviation of 12. We're gonna round up. 13 minutes. There we go. That's what that data means. I don't like to give you guys just numbers without it really having a meaning to it, because then it's just numbers. There we go. All right, how are we doing? Good, good. Okay, so then we have some uses of standard deviation. So we're going to talk about 2 theorems. You have the Chebyshev theorem, which is not really that widely used. We're not going to use it after this chapter. We are going to use the empirical rule after this chapter. Okay, so bear with me. And again, these formulas too are on, I'm not sure about the empirical rule, but I know Chebyshev's is. It's kind of fun to say, but it's not used that much. So we can find out how many total observations should fall with a given interval about the mean. So for any number k, k has got to be greater than 1, at least, here's the formula, 1 minus 1 over k squared, percent of the datas should lie within k standard deviations of the mean. Okay, so according to this theorem, find the percent of data values that should lie within 2 standard deviations of the mean for any distribution. So if k equals 2, what we would do here is we would just go, here's the formula, 1 minus 1 over, and we'd put 2 here, 2 squared, percent. So what would that give us? Well, 1 minus, what's 2 squared? 2 squared is 4. So 1/4 is 0.25. 1 minus 0.25, 75. So this would be 75%. 3, same thing. So I'd go 1 minus 1/3 squared. So 3 squared is 9. So that would be 1/9. And then 1 minus that. So 1 minus second answer. So we'll do 75. So we'll do 2 places. So 89%. This is not that widely accepted in general statistics practices. The empirical rule, however, is. Okay, you do need to know them both for the test, but this is what we'll be using when we generalize data and we put it on our normal curves in chapters 6 and on. So here's what the empirical rule tells us. It tells us that 68% of data falls within 1 standard deviation of the mean. 95% of data lies within 2 standard deviations of the mean, and 99.7% of data falls within 3 standard deviations of the mean. So sometimes this is called the 68, 95, 99 rule, but it's the empirical rule. So if we go back to what I was talking about in 3.1, 3.2, we talk about the M&Ms. All right, so we say M&Ms are normally distributed. That's in empirical rule. This is normal distribution. So M&Ms have on average 30 per bag with a standard deviation of 2. So what that means is that if I do 1 standard deviation, so I've got 30 M&Ms, so 1 standard deviation, okay, would be 30 plus or minus 2, give or take 2. So that would be between 28 to 32 M&Ms in the bag. Okay, well, that's going to be right 68% of the time. That's what this is telling you. 2 standard deviations would be 30 plus or minus 2 and 2 again. So 4, because each standard deviation would be 2. So that would be 26 to 34 M&Ms. So 95% of the time, 95% here, that's how many M&Ms will be in the bag. 3 standard deviations would be 30 plus or minus another 2, 6. 24 to 36. 99.7% of the time, there's going to be between this many in the bag. So the further you go out, the more likely you are, with this case, to pick up a bag of M&Ms and have between that number in the bag. Okay, there's always going to be that little bit outside of the norm, okay, where maybe there just was a malfunction and there's too many or too little, okay, but this is going to catch all of your data. That's the empirical rule here. You guys following? Does that example make sense? Good, good, good. Okay. All right, so we got a curve here. We're going to do well, we're going to do that on the example, I think. So I'm going to leave that for right now. Let's do the theorems first. Okay, so using the 2 theorems, how many observations are expected to follow a certain number of standard deviations from the mean? Assume you have normally distributed data for 200. How many? Okay, so in this case, you've got 200 observations. We want to know how many would fall within these. So we're using the empirical rule. So 1 standard deviation is what percent? 68. So we would go 68% of 200. That's what we're doing here. So that's 0.68 times 200. So 136. We would need 136 observations to fall within 1 standard deviation of the mean. 2 standard deviations, that would be 95% of 200. How many would that be? $190, so 0.95 times 200. And then 3 standard deviations would be 99.7% of 200. How many would that be? Yeah, so 199.4. Okay, now using Chebyshev's, same thing, 200 observations. So what was the percent with Chebyshev's theorem for 2? Do we remember? Got to go back up here. We can do the formula. We can go back up here and look. It was 75%. Okay, so this is 75% of 200. How many is that? So that would be 150. And then 3 standard deviations was 89% of 200. So we would do 0.89 times 200. So that would be 178. All right, I want to go over the normal curve with you guys before we do a problem with it. Let me see. Let me just look at this real quick. I think there was a problem with IQ, but I think it's further back. So we're going to do another problem. So you guys can come back up here to the curve. And what I'm going to do is I'm going to put a line underneath it because for some reason, hopefully your guys' has one, but this didn't print. All right, and then within that line, there should be another line like here, here and here, and then here. No, I didn't do that right. Hold on. All right, that's not going to work. Okay. It's a little uneven, but this is what we look at. Okay, so let's put this in context, the empirical rule. So we're going to go with one thing that really stands out, I think, is IQ. We'll do that. So the average IQ is 100 with a standard distribution of 15 points. Okay, I don't know if you guys have ever taken an IQ test or had a child take an IQ test, but when they do, what they'll do is they'll show you this curve and they'll say, okay, this is the normal curve and this is where you are on the curve, okay, with your percentages. So what that means is X bar is in the middle. Okay, so this right here is your mean, your X bar. And then your standard deviations are going to be on either side. So this would be -1 standard deviation, and this would be +1 standard deviation. And then this would be minus 2 standard deviations and plus 2. And then minus 3 and plus 3. So if I fill that in with this data, my X bar is 100. Okay, my standard IQ, or my average IQ. So one standard deviation above the mean, I would add 15. So that would be 115. One standard deviation below the mean, I would subtract 15. That would be 85. This value right here is that. Let's see. All of this in green here. That is one standard deviation of the mean. So what we say here is that 68%, this is 68% from here to here. 68% of people have an IQ between 85 and 115. Okay, that is what that is telling you there. Now, if we go one further, we subtract another 15, that's going to be 70, and I add another 15, that's going to be 130. So now I'm going to go from here to here. Let's see. Fill this in. Okay, so that's going to go from here. Nope. There, that is 95%. So 95% of people have an IQ between 70 and 130. Okay, and then you're going to go another 15. So if I subtract 15 from 70, I'm going to get 55. If I add 15 to 130, I'm going to get 145. And then that's going to encompass almost all of my data. So that's going to tell me that 99.7% of people have an IQ between 55 and 145. Now, just a couple of things about the curve itself. How many people have an IQ, or what percentage of people have an IQ above 100? Well, actually, let me preface this with this. The entire area of the curve, I can go beyond. See, there's a little space right there, beyond 3 standard deviations. So the entire area under the curve is 100%. Okay, so 100% under the curve. So if I split this in half, then 50% of people are going to have an IQ over 100. If that's the average, it's 50-50. 50% have IQ over 100. 50% have an IQ less than 100. I can split that curve. If this is encompassing 99.7% of the curve, then I've got okay, 0.3 that are outside of these numbers. So if I split that between having an IQ less than 55 and greater than 145, I do 0.3 divided by 2. I get 0.15. So 0.15, 0.15 on either one of these. Okay, so 0.15% of the population has an IQ over 145. 0.15% of the population has an IQ below 55. Okay, so all of these percentages will add up to 100 if I add everything out of the curve. I can do the little bits here as well. Okay, so 68% divided by 2 would be a 34% and 34%. Okay, then you would need to find the difference from 68 to 95 is, drawing a blank here, 27. If I divide that by 2, 13.5 and 13.5. And then from 95 to 99.7, that is 4.7. So if I divide that by 2, that's going to be 2.35%. 2.35%. If I add all of these numbers here in black, that's going to add to 100%. What does this mean in context? Okay, let's say your IQ is here. Let's say it's right here. Let's say your IQ is 120, 125. Okay, well, you're in this percentage of the population. So 13.5% of the population has an IQ in the same range as you. Okay, you could say that if I added everything less than that, you're, higher than 34 plus 34 plus 13.5. You'd add all of these together. So we're going to use this to answer questions. This is a very messy bell curve here, but this is going to help us just with some things. So you can say, okay, where do you fall on these curves? What is the percentage of data? All sorts of things like that. So it's a very kind of high level overview. I just spilled my coffee. That's not good. Kind of a high level overview, but we are going to go really, really, really in depth with this. So don't worry if it doesn't make sense right away. We will get to it. So give me 1 second to clean up this coffee. Let me see here. I'll be right back. I'm going to grab a paper towel. All right, I'm back. Does anybody have any questions before we go to our practice problems? All right, I am not seeing anything. So let's go ahead and do the practice. Now, what I did, yes, there is. It's attached to your packet, I believe, actually. What I did was I made this, I wanted to have more people, but there's only 10 people in the session today. So we're going to have to add some stuff in. But let me show you guys where this is. So the practice set is going to be in Blackboard. I just went ahead and posted it in the announcements. So it's right here in the announcements when you log in, 3.3 to 3.4 classwork. All right, so just for fun here, you guys go ahead. I wanted to get like at least 30 pieces of data for this, but why don't you guys tell me where you are and then I'll make up some more. We don't typically make up data. That's not a good thing, but just so we can learn how to do these calculations, we're going to. So type in. You guys can go ahead and type in. There's only thing here. So here's the thing about boundaries. If you weighed 8.4 pounds, so my son was 8 pounds 4 ounces, so we'll say 8.4, even though, you know, it's 4 out of 16. But anyway, if you weighed 8.4 ounces, are you going to be in that 7 to 8 pounds, or are you going to be in that 9 to 10 pounds? You would be in the 7 to 8. So boundaries is where you would round up or round down based on that. So like if you weighed 8.8 pounds 10 ounces, you're going to round up to 9 pounds. Okay, so let's see, we've got 1 in 5 to 6. We've got 1 in 9 to 10. I'm not sure if Hunter's telling me, but I'm just going to go ahead and mark it. 9.2. Would 9.2? Yeah, that would go here. 9.2, 7 to 8, 7 to 8, 7 to 10, 7 to 8. I think we got 2 more people. I think I was here. I'm going to put both my kids in. So we had 8 pounds 2 ounces and 8 pounds 4 ounces. 9.8. Wow. Big baby. So 6.4, would that go into 5 to 6 or 7 to 8? Very good, 5 to 6. I think you already put that. All right, so I want to have more data points. So this is where we were, but let's just say it looks like this. So we're going to go with, let's keep this, we'll go with 8 for this one. Just ignore these. We're going to say this was an example that we ran, and this one was 4, and that was 4. We're going to do 1 here and 2 here. And I don't think babies can really, I know there's very few that can survive here. We're going to say there was 0 and 0. I don't think if you're less than a pound, you can really survive. All right. So we've got our frequency chart. So let's add those together. How many data points did I get? 6, 19. All right, hold on. Let me change it. I'm changing it again. Erase. I'm sorry. I want more than that. We're going to go 0, 0. We'll do 3, 7, 10, 7, 3. No, I don't want it completely like that. Make this 10, 11. I'm sorry, guys. All right. We're going to go with these numbers. What does that add to for the sum of our frequencies? 30. Okay, so we've got 30 data points. All right, is this grouped or ungrouped data? This is grouped data, yes. Is it a population or sample? I didn't tell you. Well, there's not everybody in here, so this is a sample. All right, let's get the midpoints. We are not going to use these top 2 because nothing fell into these categories. So we're going to cross these out. Okay, so the midpoint between 3 and 4 is going to be 3.5, then 5.5, 7.5, 9.5, and that's going to be an 11.5 because you want them to be the same difference between each category. All right, so to do the, I think we're doing the mean, the variance, and the standard deviation for these. Yes. Okay. All right, so let's first do the mean. So the mean is going to be the sum of the midpoint times the frequency over sample size. So we need the midpoint times the frequency. So we're going to do 3.5 times 3. That's going to give us 10.5. Then 5.5 times 7. That's going to give us 38.5. Then 7.5 times 11. 82.5. 9.5 times 7. 66.5. And then 11.5 times 2. 23. So let's go ahead and add all of those numbers together. And that's going to be, let's see, 221. All right, next we need m squared f. Oh, let's do the mean first. I'm sorry. All right, so the sum of mf is 221 divided by n, which is the sum of f here. So 221 divided by 30, 7.37. Or we'll do 367. Okay, so the average weight of a baby is 7.367. I think that's pretty average. Now we're going to do the variance and the standard deviation. So I know they're down at the bottom, but I'm just going to write them up here so we can still see our data. So for the sample, you're going to have s squared, sum of, now I forgot, I didn't have it right in front of me, m squared f, that's this one, yeah. Minus the sum of mf squared over n, and then over n minus 1. Let me double check. Yeah. Okay, so we need m squared f. So let's go ahead and do that. So 3.5 squared times 3, so 36.75. All right, and then 5.5 squared times 7, 211.75. Then 7.5 squared times 11, 618.75. Then 9.5 squared times 7, 631.75. And then 11.5 squared times 2, 264.5. Okay, so let's go ahead and sum that column. And you're going to get 1,763.5. Everybody get that? Okay, so let's go ahead and put this into the formula. So you're going to have s squared equals the sum of m squared f, which is 1763.5, minus the sum of mf, which is 221, squared over n, 30, over n minus 1. So let's go ahead and do that. So I'm going to go in my calculator. I'm going to do 221 squared. Then I'm going to divide it by 30. Then I'm going to do 1763.5 minus this number. So minus second answer. And then I'm going to divide by 30 minus 1, which is 29. So I'm going to get 4.671. Okay, so I did this first, then divided, then my subtraction. And then I divided by 29. Okay, so my variance, 4.671, the standard deviation is going to be the square root of that number. So I'm going to go second square root of my answer, so second answer. I'm going to get 2.161. So your mean is 7.367, variance 4.671, standard deviation 2.161. So what does that mean? That in this made-up sample of birth weights, the average weight of the babies in this class, let's say it was in our class, was 7.367 pounds with a standard deviation of 2.161. Now, you can do grouped frequency in your calculator, which we haven't gone over yet. So it's not going to be the same thing as the ungrouped. Okay, so let's go over this, finding the standard deviation in your calculator. All right, so for grouped frequency, you're going to actually need two lists. So go to Stat and then Edit, and you're going to need two lists. So highlight, go up here in L1 and clear it. Now, this is very important. Midpoint is going to go first. Frequency is going to go second. Okay, so put your midpoints in first. And then scroll over, so you can just hit the to the right button. And then your frequency. Okay, so in L1, you've got your midpoints. In L2, you have your frequency. Then you're going to go to your home page, so second quit. You're going to do the same thing that you do for ungrouped. You're going to go to Stat, Calc, one variable statistics. This is still one variable statistics, okay? We're just using a midpoint as part of it. So what you're going to do here, for this calculator, for the 83, the 84 is a little bit different, all right? So I'll do this one first. So you're going to go L1, comma, L2. Okay, so here's the comma button above the 7. So you're going to do second 1 for L1, comma, second 2 for L2. And then you're going to have your data. So your X bar is 7.366 or 367. Okay, you've got your sum of MF, sum of MF squared, sample standard deviation, population standard deviation. Now, if you have the TI-84, when you hit the one variable statistics, you're going to have the, I think the first one is X list. That will always be the midpoint. And then frequency list will be the frequency. So if you put your midpoint in L1, it would be L1 in the first part. And then if you put frequency or L2 as your frequency list, it'll be L2 where it says frequency list, and then scroll down to calculate. So that's different than when you have ungrouped, where you leave frequency lists blank. So if it's ungrouped, leave that blank. If it's grouped, you've got midpoint in L1, frequency in L2. You have to reset your calculator if you deleted L1 and L2. So I forget how to do it, but if you Google it, it's pretty simple, but you'll have to reset the calculator. But you can use L3 and L4 just as L1 and L2, just when you're pulling the data for now, you have to pull it from L3 and L4. Okay. Any other questions about doing this in your calculator? And I actually have on YouTube, I have a separate video just for doing grouped and ungrouped frequency distributions. They're shorter, just if you need some extra tutorial. All right, so if we put that on the graph, we're not going to put that on the graph right now. It's, it's on there though. It's not too hard to find. All right, we're going to do one more problem. And we're going to fill this out. All right, so the mean time, I'm going to find this. I don't have this problem in here. Okay, so the mean time taken by all participants to run a road race is 120 minutes with a standard deviation of 15 minutes. Okay, create a normal curve and use the empirical rule. So we're using the empirical rule to answer questions. All right, so let's go ahead and do that. So if the mean time is 120 minutes, here's the middle. That's going to be your 120. Standard deviation of 15 minutes. So I'm going to add 15 minutes. It's 135. And I'm going to subtract 15. That'll be 105. All right, and then let's see, we'll subtract another 15, that'll be 90. And let's see here, we'll add another 15, that'll be 150. And then we'll add another 15 here, that'll be 165. And subtract another 15, that'll be 75. Okay, so we fill this out. You've got your 120. I'm going to draw a line here just to split this down the middle. Don't know why it doesn't let me grab. There we go. Kind of crooked, but it still works. Okay, so let's take a look at this. We're using the empirical rule for this. So what percentage of the population ran the race in 90 minutes or less? Okay, so if I'm splitting this up, here's my 90 minutes. Okay, so that is, let's see, here's 1, here's 2. All right, so 90 minutes is 2 standard deviations to the left of the mean. But here's what we want, 90 minutes or less. So we're actually looking for this here. Okay, we know this entire curve is 100. All right, but here's what we have. For our data, you know that 95% of the population for 2 standard deviations is from here to here. So that's 95%. Don't do that on your paper because I'm going to erase this in a sec. So that's 95%. All right, well, there's 5% that is unaccounted for. Half of that is over here. Half of that is over here. Okay, where did I get that 5%? 100 minus 95. Okay, so half of that, 2.5%, is right here, from here to here, and the other 2.5% is right here. So the percentage of the population that ran in 90 minutes or less is 2.5%. Okay, and another thing that you could do to help with this is the chart the way we had it. So remember, you had 68% was 1 standard deviation, which you split into 2, which is 34 and 34. Then you had the 95% that was 95 minus 68, and then divided by 2, so that was 13.5 and 13.5. Okay, then you had the rest here this was 2.35 and 2.35. And then you had after that was 0.15 and 0.15. Okay, that's every little segment of the population. What percentage of the population ran the race in 165 minutes or more? So if I'm looking at the graph now that I've got all of this filled out, what would that be? So it seems like we're a little confused. So let's look at 165. Here's 165. Okay, that's 3 standard deviations from the mean. Above that is this 0.15. Okay, so 0.15% ran the race in 165 or more. That means we would go greater than that. Another way we could figure that out is 165 is 3 standard deviations from the mean. Okay, so if we visualize that, all right, you've got 1, 2, 3 standard deviations from the mean, 3 on this side. We know that that's 99.7. Okay, to figure out what's missing here and here, we need to do 100 minus 99.7, which would give us 0.3. And then 0.3 would be what's left, which means I've got to split it onto either side of the curve. So if I divide that by 2, that gives me 0.15 here and 0.15 here. Okay, so drawing the curve out and visualizing where that number is really going to help us when we do these problems. What was the average time for 68% of the finishers? What's 68% represent in the empirical rule? That is, yes, 1 standard deviation. 68% is 1 standard deviation, which would be between 105 minutes to 135 minutes. Okay, if 2,000 people ran the race, how many finished in 75 minutes or less? So, is that the last question here? Yeah, okay. So what percentage of people finished in 75 minutes or less? So when I'm looking at the curve, yeah, Naya, you got it. All right, so here's the 75 or less would just be this little tiny part right here. The 99.7 would be from here to here. That would be the 99.7. So that's encompassing this entire area under the curve. So the 2 parts that are left are the 0.15 and the 0.15. That would give us 100. So we're just looking at this little curve, this little part here. So 0.15% of 2,000 people. Okay, so 0.15% would be 0.0015, because remember you take that, divide by 100, then multiply by 2,000. So 3 people. All right, and that's the end of the practice problem. Does anybody have any questions about this?